This video band is concerned with integration, which may be regarded as the reverse process to differentiation, and it concentrates on the visual aspects of the process. You'll see later how integration can be used to derive the distance travelled by this car, knowing only the car's velocity function. We shall refer in the video to a couple of features of differentiation which were introduced in the video band for MS221 Chapter C1. If you find that these don't seem familiar, then you might like to view that video band once more before completing this one. In order to visualize how the graphs of derivatives arise from those of original functions, we introduced the concept of a gradient meter, a simple device which measures gradient directly on its vertical scale. It works because the base of the gradient meter is exactly 1 unit long. So the gradient of this line is numerically equal to the reading on the scale, and the meter correctly registers gradients which are positive, or negative, or zero. To measure the gradient at any point on a curved graph, we place the meter with the diagonal piece along the tangent to the graph at that point, with the vertical piece touching the point. Then the gradient of the graph here is equal to the meter reading which appears directly beneath. By moving the meter along the curve and dropping the readings down onto another set of axes, we can construct the graph of the derivative, which is just that of the gradient. That's how we approach differentiation. But the topic of this video band is integration, which is the reverse of differentiation. Before, we were given a function, big F of x, with a graph like this, say, and we wanted to find the corresponding derivative, little f of x, whose graph can be constructed with the gradient meter. These two functions are related by the equation big F prime of x equals little f of x. For differentiation, we know big F and we want little f. Now for integration, the connecting equation remains the same, but the sense in which it applies is reversed. We know little f and we want big F. So that's what integration is all about. We're given a function, little f of x, and we seek another function, big F of x, whose derivative is the function we started from. You'll be aware by now that the results obtained earlier in the course for standard derivatives are also of prime use in integration. But finding integrals in particular cases isn't our chief concern here. You'll see the development of algebraic results and integration formulas in the text. This video band aims to explain integration in mainly visual terms. So, visually speaking, what's new? Whereas before we worked down this picture from the upper graph to the lower, we now try to move in the opposite direction, from the bottom to the top. We start with a blank upper graph, since big F of x is initially unknown and is the function we seek, but below we have the graph of some known function, little f of x. The gradient meter turned out to be a useful conceptual device in constructing derivatives. So it's natural to wonder if it might help when moving in the opposite direction. Where would we start with it? The obvious thing to do is to choose a point on the graph of little f and place the meter with its base on the x-axis and its vertical scale coinciding with the y value on the graph. That constructs a line along the third piece of the gradient meter, whose gradient is numerically the same as the y value on the graph of little f. So this is the gradient which the graph of big F should have at x. Its tangent must be parallel to this line. We can construct parallels by moving the gradient meter vertically upwards, leaving small line segment traces on the blank graph above, each of which has the correct gradient for big F at x. But which of these line segments is the right one? Remember, adding a constant to a function doesn't alter the derivative. So as we're starting with the derivative, it's difficult to pin down the function we're looking for. In fact, there are an infinite number of choices for where we place the line segment. It could be on the x-axis, or anywhere above, or below. All we know is that the graph of big F has that particular gradient when it passes through this value of x. Before we answer that question, let's find some more line segments. A similar reverse construction with the gradient meter can be carried out for any other value of x, with the same degree of uncertainty emerging in each case. Here's how it looks for a regularly spaced set of values for x. We end up with a picture consisting of many small line segments. And in principle, we could construct such a segment for any values of x and y on the upper graph. This is called a direction field, since it indicates the direction which the graph of big F must take at each value of x and y which it might pass through. You can imagine sketching a curve through this direction field, whose gradient would match that of the field at each point on the curve. If we started from here, then it would look something like this. But we could have started from somewhere else, even if we took the same starting value for x. If we start from here, then the curve looks like this. And if we start from here, then it's like this. What we have sketched here are three possibilities for the graph of big F of x. Two things may strike you about the process by which we arrived at them and about the outcome. The first is that even if we fix the starting value of x, there's an infinite number of possibilities for the starting value of y. Anywhere on this vertical line, in fact. And that means that the reverse construction with the gradient meter on its own is not enough to find a single graph for big F. The second is that the different possible graphs we've drawn look remarkably similar. In fact, they can be obtained from each other by a suitable vertical translation. And this is also true for any other possible graph of big F which could be drawn. Taking the first point, on the infinite number of starting values for y, we need more information if we're to pin down a particular graph for big F. A convenient way of doing this is to specify one point which the graph has to pass through, one value of y corresponding to one value of x. Once we've done that, it looks like it is possible to arrive at a particular graph for big F, although we'll need to think a little more later about how it is to be sketched. We call any such big F, regardless of starting point, an antiderivative of little f. It's a function for which big F prime equals little f. And the family of all the possible antiderivatives is then called the indefinite integral of little f, which is denoted by little f with an elongated s before it. That's the integral sign. Let's now turn our attention to the fact that all of the curves we've sketched can be obtained by a vertical translation of any one of them. Then we can say that if two of these antiderivative graphs differ by an amount c at the starting point, then that difference is the same at any other value of x. So, if big F of x is one antiderivative of little f of x, and c is any constant, then big F of x plus c is another antiderivative of little f of x. That's really saying the same as something which we reminded you about earlier. That if you add any constant to a function, then the new function has the same derivative as the old one did. And there's yet another interesting expression of the fact that antiderivatives of little f differ by a constant. Suppose that a and b are any two values of x. Then this vertical distance is the change in the value of the antiderivative big F of x as x moves from a to b, which is, of course, big F of b minus big F of a. But that change is the same for all other antiderivatives of little f. In fact, it can be seen as a property of little f itself, as well as of all its antiderivatives. It's the accumulated change in any antiderivative between x equals a and x equals b, given that the rate of change over that interval is given by the function little f. We call this accumulated change the definite integral of little f from a to b. And we denote this as the integral of little f with subscript a and superscript b on the integral sign. From what's been said, you can see that this is equal to big F of b minus big F of a, where big F is any antiderivative of little f. This definite integral will be positive if big F of b is larger than big F of a, and it'll be negative if big F of b is smaller than big F of a.
What we've said so far has been on a rather abstract level. Let's think a little about what this all means in a situation which you've come across before.
This car travels along a straight road. You know that if the displacement s travelled by the car is given as a function big F of time t, then the velocity v of the car is given as a further function little f of t, where little f of t is the derivative of big F of t. What we're now considering is the reverse deduction which can be made in this type of situation. If we start from a known velocity function v equals little f of t for the car, then by integrating we can obtain its displacement or position function, s equals big F of t. Up to a point, that is. In order to give a complete description of the car's position, you also need to know where it starts from, since that information is independent of what the velocity function tells you. So the indefinite integral of the velocity function gives a description of all possible motions for the car's position. And a single one of these is pinned down by specifying the starting point. Also, given two times t equals a and t equals b, the definite integral of the velocity function from a to b describes the displacement travelled by the car between those two times. Does what we said before about the definite integral tell us anything useful here? It tells us that the displacement travelled by the car between times a and b is determined completely by the given velocity function, and depends not at all on what particular place the car happens to start from.
After that interlude, to consider an application of integration, we return to a more abstract approach. But you may find it useful to consider from time to time how what we're doing relates to the example of velocity and displacement. We revert also to using x instead of t as the independent variable.
Let's think now about just how we can sketch the graph of an antiderivative to match the gradients given by a direction field. One approach is to consider how well we could approximate the curve with a connected sequence of short line segments. Let's suppose that we have a starting point, a, k, so that big F has the value k at x equals a. Then the gradient of the direction field at that point is little f of a. So the tangent to the graph of big F at a, k, has that gradient. The points on this tangent are close to points on the graph of big F itself, provided that we are not too far from x equals a. Let's take the tangent as an approximation to the curve up to a horizontal distance h away from x equals a, at which point we've risen a height h times little f of a from the starting point. Now let's use the direction field at the point we've reached to determine the gradient of our next line segment. We're now at x equals a plus h, so the gradient provided by the direction field is little f at a plus h. And after a second step h to the right, we've climbed a further height h times little f at a plus h. This process continues, with line segments being added at each stage to the right-hand end. The result is a graph made up of line segments which approximates the graph of the antiderivative that we're after. Suppose that it takes n steps to reach x equals b. After these n steps, the value of y reached by our sequence is k, that's the starting height, plus h f at a, the change at the first step, plus h f at a plus h, the change at the second step, plus h f at a plus 2h for the third step, and so on, up to h f at a plus n minus 1 times h for the nth and last step. This is an approximation to big F at b, provided that big F at a equals k. So with a small rearrangement, we've constructed an approximation for big F at b minus big F at a, which is h times the sum little f at a plus little f at a plus h plus little f at a plus 2h, and so on, up to little f at a plus n minus 1 times h. So this is also an approximation to the definite integral of little f from a to b. We can write that in sigma notation. The definite integral is approximated by h times the sum from I equals 0 to n minus 1 of little f at a plus ih. So far so good, but it is only an approximation. How can we improve on it? Well, let's try again, but this time with a smaller value of h. Even though this means that to reach from x equals a to x equals b, we'll need to compensate by having a larger number of steps. In fact, we can think of the distance from a to b in two ways. On the one hand, it's just b minus a. But it's also n steps, each of length h. That's a total of nh. The number n of steps that we need is therefore governed by the condition that nh equals b minus a. Since the two sides of this equation both have to describe the distance from a to b. Suppose, then, that we halve the step size h, and correspondingly have to double the number of steps. That would make this sum a better approximation to the definite integral of little f from a to b. Then we could halve h again, and continue doing this until our approximation to the graph of the antiderivative and to the definite integral is as accurate as required. In fact, what we're saying is that the definite integral of little f from a to b is equal to the limit of this sum as h tends towards 0, with the product nh held fixed at the value b minus a. So limits are involved in integration as well as in differentiation, though this is a more complicated type of limit. It involves values of little f throughout an interval ab, rather than just values close to a point, as for the derivative.
We reach this statement by thinking about how the graph of an antiderivative could actually be constructed. And what we've described is, in effect, an iterative procedure, which can be carried out on a computer. But this final algebraic statement is an important one. So let's think a little more about what it actually says.
We're claiming that if the continuous function little f has an antiderivative big F, or in other words, if big F is any function for which big F prime equals little f, then big F at b minus big F at a, which is also the definite integral of little f from a to b, is the limit of this expression as h tends to 0. This important result is known as the fundamental theorem of calculus.
Although it should seem plausible, as a consequence of how it was introduced, we've not come anywhere near proving it. In fact, its proof is not something which we're able to give in this course, though you will see it proved if you undertake further second-level studies in pure mathematics. We've defined the definite integral of little f from a to b as the overall change in any antiderivative of little f as x moves from a to b. In the latter part of this video band, we'll show another interpretation of this definite integral, which this time will appear on the graph of little f itself rather than on the graph of big F.
We said that the definite integral of little f from a to b is equal to this expression in the limit as h tends to 0. But let's ignore the limit part for the moment. This finite sum is an approximation to the definite integral. It can be rewritten as the sum of h f at a, h f at a plus h f at a plus 2h, and so on, up to h f at a plus n minus 1 times h. But that is just the sum of the areas of these rectangles. Base h times height f at a for the first, base h times height f at a plus h for the second, and so on. So the limit of this sum, as h approaches 0, ought to be equal to the limiting sum of areas of such rectangles. Or in other words, to the area beneath the graph of little f between x equals a and x equals b. Actually, you might regard that as a definition of what we mean by the area beneath the graph of little f. So this area is another manifestation of the definite integral of little f from a to b. But, and it's a significant but, that interpretation only holds when little f has no negative values in the interval a, b. If it takes negative values, then the identification of the definite integral as a limiting sum of rectangular areas is no longer quite correct, as some of the terms will be negative. You've seen in the text how the definite integral is then interpreted in terms of areas.
That concludes our visual survey of integration. We've shown that the definite integral of little f from a to b represents the change or accumulation from x equals a to x equals b in any function big F of x whose derivative is little f of x. We've described an iterative process which can be implemented on a computer to calculate a definite integral or tabulate values for an antiderivative. We've also shown how the definite integral of f from a to b can be interpreted as the area between the graph of f and the x-axis, provided that f is not negative in this interval. And we've introduced and hopefully made plausible to you the fundamental theorem of calculus, which links the definite integral of f from a to b to this limiting sum. Finally, here's another very practical application of integration.
The occupants of this submarine need to know their precise position at all times, but they can't see where they are while underwater. They find their position by measuring the boat's acceleration and then integrating. You might like to think about the use of definite and indefinite integrals here, and the number of integrations needed to find the submarine's position given its acceleration.